In this video, we're going to go over oxidation numbers and how to find them. So let's say if we're given the element zinc, what is the oxidation number of zinc? Now the first rule that you need to know is that the oxidation state of any pure element is always 0. So the oxidation state of oxygen gas as a pure element is 0. Fluorine gas as a pure element is 0. Even phosphorus as a pure element is 0. So if there's no charges and it's only one pure element, it's not a compound, the oxidation state will always be 0. So that's the first rule you need to keep in mind. Now the second thing is the oxidation state of ions. The oxidation state of the zinc 2 plus ion is basically the charge of what you see there. It's positive 2. The oxidation state of the Fe plus 3 ion is simply positive 3. Now sometimes you might have diatomic ions. For example, the mercury 2 plus ion. Individually, each mercury ion has an oxidation state of 1 because there's 2 of them. So you need to write an equation. 2 mercury atoms has a net charge of positive 2. So if you divide both sides by 2, you can get the individual oxidation state of each mercury particle, which is plus 1. So here's another example. This is the peroxide ion. To find the oxidation state of each oxygen atom in this ion, you could write an equation as 2 oxygen atoms with a total charge of negative 2. So individually, each oxygen atom has a charge of minus 1. So that's the oxidation state of oxygen individually in the peroxide ion. This is the superoxide ion. So if you want to find the oxidation state, you need to divide the total charge by 2. So each oxygen atom has a net charge of negative 1/2. So 2 of them combined will have a net charge of negative 1. So keep this in mind. Anytime you have a pure element, the oxidation state will always be 0. And if you have an ion, let's say if it's a monoatomic ion, the oxidation state is the same as that ion. Now let's talk about compounds. Whenever you have fluorine inside a compound, when it's not a pure element, fluorine is always going to have a negative 1 oxidation state. Fluorine is the most electronegative element. When oxygen is in a compound, it's going to have a negative 2 oxidation state unless it's bonded to fluorine or unless you hear the name peroxide or superoxide. Whenever you hear the name peroxide, oxygen has a negative 1 oxidation state. If you hear the word superoxide, it has a negative 1/2 oxidation state. But if you hear the word oxide, then the oxidation state is negative 2, which is 99% of the time. Now hydrogen will have an oxidation state of plus 1 when bonded to a nonmetal. When bonded to a metal, hydrogen will have an oxidation state of negative 1. And really, the key is electronegativity. Hydrogen is more electronegative than most metals. That's why it bears a negative charge. But hydrogen is usually less electronegative than most nonmetals. And so that's why it bears a positive charge. So typically, the element that's more electronegative is the one that usually carries the negative charge. Now let's work on some examples. What is the oxidation state of magnesium and chlorine in this compound? By the way, most halogens are usually negative 1. Chlorine typically has a negative 1 charge, like fluorine. If we write an equation, Mg plus 2Cl, this whole compound is neutral, so therefore the total charge is 0. Now, if chlorine has a negative 1 oxidation state, that means magnesium has to have a positive 2 oxidation state. You could literally solve it. And it makes sense. Magnesium is an alkaline earth metal, which typically has a positive 2 charge. Go ahead and find the oxidation states of aluminum and fluorine in this example. Well, we know that fluorine is -1 in a compound, always. And aluminum, based on where it's located in the periodic table, it's typically +3 within an ionic compound. And you could solve it too. Al plus 3F should add up to 0, because the net charge is 0. So each fluorine atom has an oxidation state of -1. So now we got to add 3 to both sides. So aluminum has an oxidation state of +3. Here's another example. Find the oxidation state of vanadium and oxygen in this compound. So this is called vanadium oxide. So whenever you hear the word oxide, oxygen has a -2 charge. So we got 2 vanadium atoms plus 5 oxygen atoms with a net charge of 0. So each oxygen atom has an oxidation state of -2. 5 times -2 is -10. And then add 10 to both sides, so 2V is equal to 10. Next, divide both sides by 2. So 10 divided by 2 is 5. And so the oxidation state of vanadium is +5. Now let's go over some examples containing polyatomic ions. Consider sulfate. What is the oxidation state of sulfur in sulfate? Well, we know oxygen is usually -2. So let's write an equation. Sulfur plus 4 oxygen atoms has a net charge of -2. So each oxygen atom has an oxidation state of -2. And 4 times -2, that's -8. Next, we need to add 8 to both sides. -2 plus 8 is +6. So this is the oxidation state of sulfur in sulfate. Let's look at another example. Phosphate. Go ahead and find the oxidation state of phosphorus in phosphate. So once again, oxygen is still -2. So we got a phosphorus atom plus 4 oxygen atoms, and the net charge is -3, based on what we see here. So it's going to be P plus 4 times -2, and 4 times -2 is -8, and then add 8 to both sides. So -3 plus 8, that's going to be +5. And that's the oxidation state of phosphorus. Let's look at another example. Let's try nitrate. And also chlorate as perchlorate. Go ahead and find the oxidation state of nitrogen and chlorine in these 2 polyatomic ions. So we have a nitrogen, 3 oxygen atoms, and that's going to equal a net charge of -1. So O is -2. 3 times -2 is going to be -6. And -1 plus 6, if we add 6 to both sides, that's going to be +5. So that's the oxidation state of nitrogen. And for chlorine in perchlorate, it's going to be Cl plus 4 oxygens equals a net charge of -1. So this is going to be 4 times -2, which is -8. And then -1 plus 8, that's going to give us an oxidation state of +7. So now you know how to find the oxidation states of elements within compounds and polyatomic ions. Now, I want you to understand the concept of electronegativity and how it relates to oxidation numbers. Electronegativity increases towards fluorine on a periodic table. So as you go up and to the right, the electronegativity increases. So let me give you some values of common elements. So let's say hydrogen is somewhere in the corner over there, and then we have boron, carbon, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, phosphorus, and sulfur. Hydrogen has an electronegativity value of 2.1. For boron, it's 2.0, carbon is 2.5, and then 3.0, 3.5. Fluorine's the highest, it's 4.0. Phosphorus, it's 2.1, it's the same as hydrogen. Sulfur is 2.5, chlorine is 3.0, and this is 2.8, iodine is 2.5. So keep these values in mind. So here's a question for you. What is the oxidation state of oxygen and fluorine in oxygen difluoride? Now, oxygen has an electronegativity value of 3.5. Fluorine is 4.0. So which one is more electronegative? Electronegativity is the ability of an atom to attract electrons to itself. So fluorine is going to pull on electrons in its molecule. It's going to have a stronger pull than oxygen. So fluorine is going to acquire a partial negative charge, whereas oxygen is therefore going to acquire a partial positive charge because fluorine pulls on the electrons stronger than oxygen can. So in this example, oxygen will not have its typical charge of -2. The only time oxygen will have its oxidation state of -2 is if it's the most electronegative element in that compound. If it's not, then it's going to have a positive oxidation state. Keep in mind, anytime fluorine is in a compound, it has an oxidation state of -1. And the reason for that is because fluorine is the most electronegative element on a periodic table. So now we can solve for oxygen. So O plus 2F should have a net charge of 0 because there's no number here. So fluorine is -1. 2 times -1 is -2. So if we add 2 to both sides, oxygen is going to equal +2, which makes sense because it's partially positive in this particular example. Now let's look at 2 other examples, hydrochloric acid and sodium hydride. Chlorine has an electronegativity value of 3.0. Hydrogen is 2.1. And sodium, it's like 1 point something. I'm not sure what the exact number is. It could be like 1.5, 1.7, but I know it's less than 2. So in this example, hydrogen bears a partial positive charge. Chlorine bears a negative charge because chlorine is more electronegative than hydrogen. So therefore, chlorine is going to have its oxidation state of -1, which is typical of most halogens. Hydrogen is going to have an oxidation state of +1. As you mentioned before, whenever hydrogen is bonded to a nonmetal, the oxidation state is usually +1. Now what about in sodium hydride? Well, we know that sodium is an alkali metal, which always have a +1 charge. So therefore sodium is going to have an oxidation state of +1. But hydrogen has an oxidation state of -1. Typically, when hydrogen is bonded to a metal, it usually has a -1 oxidation state. And it makes sense because hydrogen is more electronegative than most metals. So it usually bears the partial negative charge. That's why it has a negative oxidation state. Sodium has the positive charge, so it has a positive oxidation state. And so you could use electronegativity to help you determine what the oxidation state will be. So let me give you another example. BH3. What is the oxidation state of boron and hydrogen? Feel free to try that one. Now hydrogen has an electronegativity value of 2.1 and boron is 2.0. Now is boron a metal or a nonmetal? In this example, hydrogen is more electronegative. So hydrogen bears the partial negative charge, or boron bears the partial positive charge. So therefore, hydrogen is going to have its oxidation state of -1 because it's more electronegative than boron. So then this is going to be B plus 3H, which is equal to 0. So 3 times -1 is -3. So boron is going to have an oxidation state of +3 in this example. Now let's consider these two examples. Sulfuric acid, or rather hydrosulfuric acid, and also sulfur dioxide. Now hydrogen has an EN value of 2.1. Sulfur is 2.5, and oxygen is 3.5. So in sulfur dioxide, oxygen has the partial negative charge, sulfur has the partial positive charge. Now in H2S, hydrogen has the partial positive charge, sulfur has the partial negative charge. Now in the periodic table, when you have elements like nitrogen, oxygen, fluorine, typically nitrogen has a -3 charge, oxygen -2, fluorine -1. Sulfur too. Sulfur usually has a -2 charge if sulfur is the more electronegative element. So looking at H2S, hydrogen is bonded to a nonmetal that is more electronegative than itself. So hydrogen is going to have the +1 oxidation state. And there's two of them. So sulfur in this example has its normal oxidation state of -2. So you can base your answer on a periodic table if sulfur is the more electronegative element. Now in SO2 you can't do that because sulfur doesn't have the partial negative charge, so you can't base the charge on a periodic table. You can do so, however, for oxygen, because oxygen is the electronegative element in that compound. So you can use the -2 charge for oxygen. So oxygen is going to have an oxidation state of -2, and to find it for sulfur, it's going to be S plus 2 oxygen atoms equals 0. So that's 2 times -2, which is -4. So sulfur is going to have a positive oxidation state of 4 due to the positive partial charge. So elements that are less electronegative, typically those are the ones you got to solve for. The ones that are more electronegative, you can find a charge based on a periodic table if they carry a negative charge. Now let's look at some other examples. NH3 and NO2. Go ahead and find the oxidation state of each element. Now, in ammonia, hydrogen has an EN value of 2.1, but nitrogen is more electronegative. It's 3.0. So therefore, nitrogen should have its normal charge of -3. If we write an equation, N plus 3H is equal to 0, hydrogen is going to have a +1 charge. It's partially positive, whereas nitrogen is partially negative. So typically when hydrogen is bonded to a nonmetal, it's usually +1, which means N has to be -3. So as you can see, nitrogen is the electronegative element in this example, and it has its periodic charge of -3, which you could find it in periodic table. Now in this case, O is more electronegative, so nitrogen is going to have a different oxidation state. It's not going to be its natural oxidation state of -3. So in this example, it's going to be +4. So typically, when you have elements like nitrogen, sulfur, phosphorus, if they carry an element that's more electronegative than itself, those are the elements you got to solve for. The one that usually has a partial positive charge. Now try these two examples, methane and carbon dioxide. In methane, hydrogen has a +1 charge. Hydrogen is less electronegative than carbon, so it's going to be partially positive. Carbon is going to be partially negative. So solving for carbon, we have C plus 4H is equal to 0, So that's 4 times 1. So C is negative 4. So when carbon is bonded to hydrogen, carbon has a negative oxidation state. But when carbon is bonded to oxygen, it's going to have a positive oxidation state. When it's bonded to hydrogen, it has a negative oxidation state. So oxygen is negative 2, and there's 2 of them, so carbon's going to have to be positive 4 in this example. Now sometimes you might have elements that have an average oxidation state that's not a whole number. Let's try these two, C3H8 and Fe3O4. In this example, hydrogen is less electronegative than carbon, so it's going to be positive 1. So if we write the formula 3C plus 8H is equal to 0. So that's going to be 8 times 1. And if we subtract 8 from both sides, 3C is equal to negative 8. So carbon, on average, has an oxidation state of negative 8 over 3. Now let's do the same thing for Fe3O4. So we got 3 iron atoms and 4 oxygen atoms with a net charge of 0. So oxygen has an oxidation state of negative 2. So 4 times negative 2, that's negative 8. And if we add 8 to both sides, we're going to get this. So Fe has an oxidation state of 8 over 3. So 8 over 3 is about 2.67. Now keep in mind, an individual iron atom cannot have a charge of 2.67. It's usually a whole number, like positive 2 or positive 3, because electrons and protons, they basically have numerical charges. An electron has a charge of negative 1, a proton has a charge of positive 1. So a typical ion won't have a decimal charge. So what does it mean that the average oxidation state is 2.67? So what is meant by that? In this compound, there are 3 iron ions and 4 oxygen ions. Each oxygen has a charge of negative 2. So the total negative charge is negative 8. In order for the compound to be electrically neutral, the total positive charge has to be positive 8. Iron metal has 2 common oxidation states, positive 2 and positive 3. Now they all can't be positive 3 because 3 plus 3 plus 3 is 9. And they can't all be positive 2 because 2 plus 2 plus 2 is 6. So some of them is positive 2 and some are positive 3. So the question is, how many iron ions have a plus 2 charge and how many have a plus 3 charge? In order to get up to 8, 2 of them has to have a positive 3 charge and 1 of them has to have a positive 2 charge. If you average the numbers 2, 3, and 3 and divide it by 3, that's going to be 8 over 3, which averages out to 2.67. So whenever you get a decimal value, what it really means is that that's the average oxidation state. Individually, some are positive 3 and some are positive 2. So the individual ions should have a numerical oxidation state. But when you have multiple of them, the average could be a decimal value because they don't all have to be the same. They can be different. So hopefully this makes sense in terms of why some oxidation states have a decimal value. Now let's try polyatomic ions that have 3 different elements in it. Go ahead and find the oxidation state of every element in that polyatomic ion. So oxygen has an oxidation state of negative 2. Hydrogen is positive 1 when it's bonded to nonmetals, usually. So all we got to do is find sulfur. So H plus S plus 3 oxygen atoms has a net charge of negative 1. So hydrogen is 1, oxygen is negative 2, and so 3 times negative 2, that's negative 6. And then 1 plus negative 6 is negative 5. So now let's add 5 to both sides. -1 plus 5 is +4. So in this example, sulfur has an oxidation state of +4. Go ahead and try this one, K2CrO4. Find the oxidation state of every element in that example. So we have 2 potassium atoms, a chromium atom, and 4 oxygen atoms. Now we know oxygen is going to have an oxidation number of -2. Potassium is an alkali metal, which all of them have a +1 charge. Chromium is the transition metal, and it has a variable charge, so that's the one we got to solve for. So this is going to be 2 times 1 plus Cr plus 4 times -2, and all of that is equal to 0. So 4 times -2, that's -8, and 2 plus -8 is -6. So therefore, in this example, chromium has an oxidation state of +6. Try this one, potassium bicarbonate. Find the oxidation state of carbon in this example. So we know oxygen is going to be -2, potassium, an alkali metal, is +1, and hydrogen is actually bonded to the oxygen in bicarbonate if you were to draw the Lewis structure. So therefore, hydrogen is bonded to a nonmetal through a covalent bond, and so it's going to be +1. So we have K plus H plus C plus 3O, and that's equal to 0. So K is +1, hydrogen is 1, and oxygen is going to be 3. Well, oxygen is -2, but we got to multiply that by 3. So 1 plus 1 is 2. 3 times -2 is -6. And then 2 plus -6, that's -4. So in this example, carbon is +4. Potassium bicarbonate, you could break it up into 2 ions, K plus and HCO3 minus. So just by looking at K plus, that tells you that K has an oxidation state of +1. Now, bicarbonate is basically the sum of the hydrogen ion and the carbonate ion. So therefore, you can see that hydrogen in this example also has a +1 charge. And then from this, you could find the oxidation state of carbon. You could say C plus 3O has a net charge of -2. And then you have to add 6 to both sides. So -2 plus 6 is +4. So if you understand the ions and all the polyatomic ions, you could break it down individually to see that hydrogen has a +1 charge in this example. And the same is true for K. So that's why it's good to know the polyatomic ion sheet. Now I have 2 more examples for you. BrCl3 and IBr5. Find the oxidation state of every element in this example. So most halogens, like fluorine, chlorine, bromine, iodine, they typically have a -1 charge. But both bromine and chlorine can't be negative. So which one is negative and which one is positive? Keep in mind, bromine has an electronegativity value of 2.8. Chlorine is 3.0. Iodine is 2.5. So in this example, chlorine bears the partial negative charge. Bromine is partially positive. So therefore, chlorine is going to have its natural oxidation state of -1. Bromine, we need to calculate it. So it's going to be Br plus 3Cl, and that's equal to 0. So this is going to be 3 times -1, and so we can see that bromine has an oxidation state of +3. Now, in the second example, Bromine is going to carry the partial negative charge. Iodine carries the partial positive charge. If it's written correctly, usually the electropositive element is written first. The electronegative element is written second. So the one that you see on the right side is usually the one that carries the natural charge that can be found on the periodic table. So in this case, bromine is going to have its natural oxidation state of -1. So iodine is going to have an oxidation state of +5 in this example. So hopefully you understand the relationship between electronegativity and oxidation numbers. So that's it for this video. Thanks for watching and have a good day.